And okay, so we're back, and I start the stopwatch, and I want to find my 4-level laser. Yeah, there it is. And there was one. Okay, so yeah, so I want to compare 3-level and 4-level laser systems, right? So let's go to 041622. Okay, so compare 4-level with 3-level. And one thing that you want to, so let's remind ourselves what the 3-level 3-level thing was. So I mean, before I stick in numbers, for the 3-level laser, I had this relation, the delta n. So let me write down here. 3-level. Okay, so delta n, it's written out here, is p minus gamma 21 over p plus gamma 21 n. Okay, and this was the condition for gain greater than 0 in steady state near threshold. So just remember, those are the conditions that we normally analyze, do all our analysis at. The steady state and then the threshold. These are the things. So from this, I can actually find the threshold power, and I will put in numbers like I did last time, but this threshold power, P threshold, for the 3-level that is required just by rearranging this, so P threshold minus gamma 21 n. I mean, at threshold, the delta n will be 0, and it's just beginning to be greater than 0. So at threshold, this is a equality, and what I have is this is equal to P threshold plus gamma 21 n. And so I can solve for P threshold, 3-level, and this works out to gamma 21. Sorry, this is a delta n. So this works out to n plus delta n over n minus. Okay, so this is one condition. This is the threshold power required for the 3-level atom. And the reason I'm doing this comparison is that, I want, because there's something that will just pop right up when you compare the 3 and 4-level atoms. So, okay, now let me do the same thing for the 4-level. For the 4-level, once again, delta n is equal to n2 minus n1, and if we do this in the, we just had this condition up there that gamma 10 is much, much larger than gamma 21 and the pump rate. And so then in that case, the n1 became 0, and n2 we have already written out here is p over gamma 21 plus p n. So that's delta n. So once again, I can solve for, do the same thing, that therefore delta n times gamma 2, 1 plus p equals p times n at threshold, right? Everyone with me here? So therefore at threshold, this is a, this doesn't, so it's equal to 0, I suppose. I mean, so that means that the delta n is equal to 0. So that means I can write this, okay? It's an equality is what I mean at threshold. And so what does this tell me? This tells me that the p threshold, and this time this is for the 4-level, okay, I can solve for that. And what you'll notice is that you get gamma 2, 1 delta n over n minus delta n, okay? So notice that, okay, so now if I compare the two, notice what's going on here. The expressions look very similar, like this is the same, the denominator is the same, but look at what happens here. You have a total number plus, what's that? Oh, sorry. Look what happened here. The difference is in this term versus this term, right? So if I do a straight comparison, then the p threshold for the 4-level divided, divided by the p threshold for the 3-level is, everything's going to cancel, and you're left with a delta n divided by n plus delta n. Okay, and of course, the inversion, delta n is always going to be much smaller than the total number. Okay, so because remember that the total number is n naught plus n1 plus n2, right? So there's a lot of stuff in 0. And so the total number, I mean, the inversion is only n2 minus n1, but the total is all these three together. And so, this is always much, much less than 1, because the delta n is much, much less than the total n. Okay? So, meaning that in principle, this is, I have not put in any numbers. This just shows, that in principle, a 4-level atom laser, 4-level atom laser, always has a significantly lower pump threshold requirement. Than a 3-level atom laser. Okay, so so I guess at this point now we just have to put in some numbers for a real laser. Okay, and so can I remove this page? Is everyone okay with this page?
Yes.
Okay.
Yes.
Okay. Good. Thank you. So now let me look at a real laser, and let's, yeah. So in a real laser, so now let's ask the question. 04, 16, 23. Okay, and so now we're gonna ask the question that I just need to remove this to the side. All right. So just like the 3-level atom laser, let's calculate. Again, ask the question. Ask for a 4-level laser now. The question is that what's the minimum pump power? Remember, we talked about this pump power per unit volume, so the power density required for lasing at threshold. So those are the two conditions we always impose: at threshold, in steady state. Okay. So, and of course the answer is again, just like last time, it's the number of pump photons absorbed per second over the volume. Okay, and so that's the number per unit volume, but I want the power per unit volume, and so the power means that I have to multiply this by the energy in each photon. So H mu, and this is between the 3 and the 0 transition, right? So now I look at my, where's my 4-level system? Yeah, here we go. So I pull that back up, okay? And so this is the neodymium ion. I guess you need a little more. Okay. And so let's look at this. So I look up a book to find that up till the lower level here, this is 1.63 electron volts. Okay, that's the energy gap. And then from the top there to the ground again, this gap is 3.13 electron volts. So basically the photons that are being absorbed, between level 0 and 3 range from 1.63 electron volts to 3.13 electron volts. So, you just take an average to get the, so what we're going to say is that the H mu 30, it corresponds to the average of, so whatever that works out to, it works out to 2.38 electron volts. So that's what I'm going to use in here. Okay, so let's just do that. And we remember what an electron volt is, right, in terms of, anyway, so we know that this guy is going to correspond to 2.38 electron volts. And I need to now make this go back. Okay, and so now what is the number of, just like we did this last time, number of pump photons absorbed per second. Well, the rate is P, and the number absorbed per unit volume would just be how much you have in the level 0 in the steady state, right? And so there you go. And then I look up the, what is P times N naught, and I just work those things out here. So Um, so you notice that P times N naught there is equal to the N2 population steady state times gamma 2, 1. Okay, so this is gamma 2, 1 and 2 steady state. This is not H bar, I'm sorry, this is just H. It's with a nu, right? It's not with an omega. So there. Let me just number this so that 4, this is equation 5. So from equation 5, on previous page. All right. And so now this N2 steady state, well, you know, this is, it's the same as N2 minus N1 steady state because N1 steady state is 0. And so this is actually equal to delta N. Okay. And so therefore, my answer here is that the power per unit volume and the minimum power per unit volume required, and the minimum is ensured because I'm using the steady state here. Well, this value here, the minimum is ensured, not because of that, but the minimum is ensured because this was evaluated, this whole thing was done near threshold, right? So minimum happens because this was done in the steady state near threshold. That's where I got this condition here, okay? So the minimum power per unit volume required for a 4-level laser is equal to gamma 2, 1 delta N H nu 30. All right. And just to remind you, I mean, you can compare this. So this is our, we'll put numbers into this formula right here. Okay, so we'll compare this to the ND YAG laser here. Okay, but I just wanted to also just say that, you know, if you compare with the 3-level, then what had we gotten for the 3-level? For the 3-level, we had, here's the, okay. So for the 3-level, we had, I'm looking at this expression here. We had the power per unit volume, minimum, right? For the 3-level, we had found was 1/2 H nu 3, 1, and there was a gamma 2, 1 there also. So far it looks kind of the same, right? I mean, the 1/2, forget that. But there's a H, there's a nu 3, 1, or in this case 3, 0, there's a gamma 2, 1. But then, instead of the delta N, you actually had a N here. And that's the difference. Okay, just as I commented in the previous slide, you know, that's the whole difference. It's the N versus the delta N, right? You remember this? You see this? It's the delta N versus the N. Okay, and that's where the whole difference arises. So anyway, let's look at the numbers now. And just for comparison, I'll also write down some of the Ruby laser numbers on the right. Okay, so what do we have? The ND YAG laser. Well, gamma 2, 1 is 4400 per second, and that actually is larger, so it's going the wrong way. It's larger for Nd:YAG compared to Ruby, okay, because Ruby, if you recall, was 500 per second. So I mean, Ruby really needed the other parameters to come to its rescue, to be able to achieve lasing. But the Nd:YAG laser, this number is actually not good for it compared to Ruby. But then let's look at now the density here. The N is, again, it's the density of the dopant, the neodymium 3+ ions, because they are the ones who do the lasing in the YAG crystal. Okay, and similarly for Ruby, it was N was the density of the chromium ions. In the what was it, aluminum garnet or something, aluminum oxide crystal. Okay, and how are the numbers? Well, for the other guy, for the 3 level, it was this was 1.6 times 10 to the 19 per cc. How about the neodymium ions in the YAG? Well, this is pretty comparable. It's 2 times 10 to the 20. So that's not too far. I mean, okay, so it's a little bit more. All right, about a factor 10 more. But then what about the delta N? Because that's what shows up here. And the delta N, it turns out, is only about 0.01%, meaning 0.01% of that is what the inversion is. So you don't, because there's a lot of atoms stuck in the 0 level, and the inversion between 1 and 2 is only 0.01% of that. So this is so this becomes 2 times 10 to the 20, right, per cc, multiplied by 0.01%. So that's 10 to the power minus 4. And so this is 2 times 10 to the 16 per cc. Much smaller than the N in the chromium, of the chromium. And so now you can, and that's where you win, because this delta N is much smaller than the N that was used in the 3 level. So there you have it. So now the numbers, that's just a matter of plonking in the numbers. Let's do that calculation. And it's very important to know how to do these calculations, meaning, you have to feel comfortable with converting electron volts and stuff to joules and whatever. But you are comfortable with that already. So the gamma 21 is 4400. Okay, and so we're going to get a nice little answer here that's much smaller than the final answer for Ruby, which, if you remember, so this is going to be a nice conclusion, better than any meme you could possibly share amongst yourselves right now. This would, what was it for Ruby? We worked it out to be the power per unit volume minimum 3 level worked out to be, I'm just copying off it was 1 kilowatt per centimeter cube. That's what you needed. And then the power absorbed by the 5 centimeter long, 2 millimeter wide Ruby rod worked out to 600 watts. Okay, so that was the result for the Ruby. Now let's do the Nd:YAG. So this is 4400 per second multiplied by the delta N, which we worked out to be 2 times 10 to the 16 per cc, but that means a further 10 to the 6 per meter cube. Okay, And then what else? Then the H nu 30. Well, the H nu 30 we said is 2.38 electron volts. So that means 2.38, and 1 electron volt is 1.6 times 10 to the minus 19 joules. Okay, so that's it, and this works out to 33 watts per centimeter cube, to be compared with the 1 kilowatt per centimeter cube there. And if you use a 5 centimeter long, similar to the ruby rod, 5 centimeter long, 2 millimeter wide ND-ag rod, then the power absorbed works out to, so you just multiply it by the volume there, and it works out to 20 watts. But here's the other thing, that the power output in an ND-ag laser is, the power output, and there are other reasons for this, but the power output is typically watts. And you remember that I had said that the power output for the ruby laser was a few milliwatts. Okay, so this is a very good example showing that the four-level laser rocks. Okay. These equations that we wrote down to analyze the four-level and the three-level laser, this is all that laser engineers do in terms of the theory. The rest is, of course, then, building lasers and finding good materials and stuff. Good materials that help you to exploit these relations to the fullest. But the equations that they use is exactly what we just wrote down, those rate equations. So if you know how to write a rate equation, you can be a laser engineer, like right now. All right. And that does conclude what I wanted to talk about four-level lasers and three-level lasers. We will now jump into a different topic next week, and I will tell you about it. There's a little bit that you have to read and understand about the frequency narrowing for the diode laser in the lab, and there are good notes for it out there. And I'll just, that's what you'll have to do kind of on your own. In the lectures, we will start on a different topic, we'll discuss that next week. All right, so that ends this, and let me stop the sharing. Oh, first of all, I need to